Hi everyone, welcome back to my channel. So today we are going to discuss the concept that is phasors. Phasor. Phasor is nothing but it's a vector rotating in an anti-clockwise direction over its origin with an angular velocity that we can call it as a phasor. Here the magnitude of a phasor, which represents the peak value of a varying quantity. Here varying quantity in the sense we are considering here alternating voltage and alternating current. These two are a varying quantity. The magnitude of alternating current or alternating voltage that represents the peak value of this varying quantity. We are going to observe the different cases of phasors. First one, if you observe a phasor diagram, this represents a voltage wave and this represents the current wave with respect to omega t. Is it right? So here, according to the statement, it is a vector rotating in anti-clockwise direction. Is it right? We know that the statement, it's a vector rotating in anti-clockwise direction about its origin. Therefore, this represents an origin. It rotates in anti-clockwise direction. We are going to observe the different cases. That is case number 1. So this represents a voltage and this represents a current. So how we are going to get this one, we will discuss later one by one. And even we are going to observe a second case, that is case 2. Case 2. So this represents a voltage and this represents the current. The angle between this omega t and this one is a pi by 2. Here also we are going to get pi by 2. So how these phasors diagrams we are going to get, that we'll discuss by considering a resistor, capacitor and inductor. And that the first one is alternating voltage applied to a pure resistor. Now let us consider a resistor which is connected to that AC source, and this is an AC source we can consider, and this represents a resistance of a resistor that can be represented by R. When it is connected to that AC source, the current flows through a resistor. Now here the alternating voltage across AC source that can be represented by expression V is equal to V naught sine omega t, where V represents the instantaneous voltage, V naught represents the peak value of a voltage, and omega that represents angular frequency. Now when the current flows through a resistor, the voltage across a resistor that can be written as voltage across resistor that can be written as V is equal to I into R according to Ohm's law. Now let us consider this one as an equation number 1 and this represents the equation number 2. Therefore, so from equation 1 and 2 we can represent IR, which is equal to V naught sine of omega t. If we simplify this one, I is equal to V naught sine omega t divided by R. So now this can be written as I is equal to I naught sine omega t. So let us consider this one as an equation number 3. If we compare equation 1 and equation 3, so we are going to observe that these two waves, voltage wave and the current wave, these two waves are in phase, because there is no difference in these two equations. We are going to observe a graph for this one, a waveform. Let us consider this is an voltage wave and these represents a current wave, right? And this represents current wave, voltage or current along y-axis and omega t along x-axis. Now these voltage and current waves start from origin and it reaches a maximum at the same time and it reaches a minimum at the same time, and again in negative side maximum at the same time and the minimum at same time. Therefore these two are in phase, in the sense the phase difference between voltage and current which is equal to 0. Phase difference is equal to 0. So this is about alternating voltage applied to a pure resistor. So we know that when alternating voltage applied across a resistor, we are going to observe the waveform like this. Already we studied, and this is a voltage wave and this represents the current wave. So here the phase difference between voltage and current is equal to 0, and the Phasor diagram for this voltage alternating voltage applied to a pure resistor, Phasor diagram is this one. Here this represents a voltage wave and this represents a current wave, the phase difference which is equal to 0. Therefore we are going to observe the Phasor diagram for alternating voltage applied to a pure resistor. And the next concept is power in purely resistive circuit. Purely a resistive circuit. Now, when the current flows through a resistor, there is a loss of electrical energy. In a sense, we are going to use the word dissipation of electrical energy. Here, the power in a purely resistive circuit, the instantaneous power at any instant of a time that can be represented by P is equal to V into I. We know this one. P is equal to V into I. But according to that the waveform of voltage and waveform of current, we know that V can be written as V naught sine omega t and I can be written as I naught sine omega t. So this can be written as V naught I naught sine square omega t, and this represents instantaneous power. Now the average power for overall one complete cycle that can be represented by P bar, which is equal to that integration of 0 to t V naught I naught sine square omega t divided by integration of 0 to t dt. Now this can be written as is equal to V naught I naught outside and integrate in the range 0 to t sine square omega t divided by, if we integrate this one, we are going to get t. Now average power which is equal to V naught I naught divided by t. So if we integrate this one sine square omega t, or integration of 0 to t sine square omega t, that can be written as 1 minus of cos 2 omega t divided by 2 into dt. So let us consider this one as a dt into dt. Now if we simplify this one, average power which is equal to V naught I naught divided by t. Now this one can be written as integration of 0 to t, multiply this one dt divided by 2, we are going to get minus of integration of 0 to t cos of 2 omega t divided by 2 into dt. We are going to average power that can be written as V naught I naught divided by t. If we integrate this one dt divided by 2, we are going to get t divided by 2 in the range of 0 to t minus of if we integrate this term. So cos of 2 omega t, we are going to get a sine of 2 omega t divided by 2 into 2 omega, we are going to get 2 into 2 omega in the range of 0 to t. Now average power, which is equal to V naught I naught divided by t into t divided by 2, we are going to get, if we substitute here, if we substitute a 0, 0 divided by t is 0, minus of, here we are going to get sine of 2 pi divided by t into t divided by 4 2 pi divided by t, we are going to get, and this t gets cancelled. So here 4 pi we are going to get sine of 4 pi value, that becomes 0. Sine of 4 pi value, that becomes a 0. Therefore the overall term becomes 0. So here we are going to observe tt gets cancelled. Average power, which is equal to V naught I naught divided by 2. This can also written as average power is equal to V naught divided by square root of 2 into I naught divided by square root of 2, and this can be written as Vrms into Irms. We can also represent it as I square Rms into R. So this represents that power in purely resistive circuit. So next concept is alternating voltage applied to pure capacitor. Alternating voltage applied to pure capacitor. So let us consider a capacitor which is connected to that AC source. So V is equal to V naught sine omega t, the voltage of a AC source, and the capacitance of the capacitor, that can be represented by Q, and the charge of a capacitor, that can be represented by Q. When the current is passes through that capacitor, so what happens, that we'll discuss now. Now alternating voltage across AC source is equal to V naught sine omega t, where V represents the instantaneous value, peak value V naught, omega that represents angular frequency. Now voltage across a capacitor, when the current is passes through that capacitor, the voltage across a capacitor, voltage across capacitor, that can be represented by V is equal to Q divided by C. Now this can be written as Q is equal to V into C. This Q can also written as V naught sine of omega t into C, because V is equal to V naught sine omega t. Now if we differentiate this one, dq divided by dt, which is equal to V naught into C, these are the constant term. If we differentiate sine of omega t, we are going to get cos of omega t into omega. Now this can be written as dq divided by dt, which is equal to V naught C omega cos of omega t. dq divided by dt in the sense of current, the rate of flow of charges through a conductor with respect to time, that we can call it as current. Here V naught divided by 1 over omega c into cos of omega t. I is equal to V naught divided by 1 over omega c, that can also written as chi c. Cos of omega t, that can be represented by sine of omega t plus of pi by 2. Let us consider this one as an equation number 1, and this represents equation number 2. This can also written as, instead of V naught divided by chi of c, we can represent I naught sine of omega t plus of pi by 2. Let us consider this one as equation number 3. Now compare these equation 1 and 3. We are going to observe there is an extra term, that is pi by 2, that represents phase or the phase difference between voltage and current. Here we are going to observe the Phasor diagram for alternating voltage applied to a pure capacitor. Already we discussed this Phasor diagram, and this represents for voltage wave, and this represents for the current wave. Here it is omega t, and the angle between voltage and current wave is pi by 2. So already we discussed phasor in the sense it's a vector rotating in anti-clockwise direction. So rotating in anti-clockwise direction, therefore we are going to observe current leads voltage by pi by 2. Current leads the voltage by pi by 2. Therefore we are going to observe the diagram or the waveform for current and voltage. We are going to observe like this. Let us consider this is an voltage wave, and the current wave is starts before a voltage wave, and this represents a current wave, but the phase difference between voltage and the current wave is pi by 2, and that can be represented by this expression, equation number 3, and this is about alternating voltage applied to a pure capacitor. Based on this, they explain capacitive reactance. Capacitive reactance. So we took in equation number 2, and this represents a capacitive reactance. So chi C. The capacitive reactance is nothing but the effective opposition offered by the capacitor to the flow of alternating current, that we can call it as a capacitive reactance. The capacitive reactance that can be represented by C, the effective opposition offered by the capacitor to the flow of current. So this we are considered 1 omega into C, 1 divided by omega C we took as a capacitive reactance. So omega that can be written as 2 pi into nu into C. So we are going to observe the relation between capacitive reactance and the frequency. The capacitive reactance is inversely proportional to that frequency. As the frequency increases, the capacitive reactance goes on decreases. If you observe the graph for capacitive reactance and the frequency, as the frequency increases, the capacitive reactance decreases. We are going to observe the graph like this. And even we know for direct current or DC, the frequency which is equal to 0. If the frequency which is equal to 0, if it is in denominator, therefore the capacitive reactance is maximum. Therefore the capacitive reactance which is equal to infinity. So this represents the capacitive reactance. The next concept is alternating voltage applied to pure inductor. Here inductor in the sense it's a device which allows steady flow of current through it, that we can call it as an inductor. When this inductor which is connected to that AC source, so this represents V is equal to V naught sine omega t, and the inductance of inductor that can be represented by L, and the current flows through it. Alternating voltage across AC source, so that can be represented by V is equal to V naught sine omega t. Now when the current passes through the inductor, the voltage across inductor, that can be represented by V is equal to minus of L di divided by dt. Here di divided by dt in the sense rate of flow of current with respect to time. Here minus sign that represents when the current passes through that inductor, that I have to consider the minus sign. So according to that Kirchoff's law, Kirchoff voltage law, that explains applying Kirchoff's voltage law. So voltage law that represents the sum of IR products which is equal to 0. So let us consider V plus of VL which is equal to 0. Here V is equal to minus of VL we are going to get. We know that V is nothing but V naught sin omega t, this one. VL in the sense minus which is equal to minus into minus, that becomes a plus L di divided by dt. Now this can be written as di which is equal to, just cross multiply it, V naught divided by L sin of omega t into dt. Integrating on both sides, if we integrate this one, V naught divided by L sin of omega t into dt, we are going to get I which is equal to V naught divided by L is a constant term. So if we integrate sin of omega t into dt, so I is equal to V naught divided by L. If we integrate a sin omega t, we are going to get minus of cos omega t. And if we integrate omega t, that we are going to get 1 divided by omega. Therefore, I is equal to V naught divided by L into omega minus of cos omega t. This minus of cos omega t, that can also written as V naught divided by L omega minus cos omega t, that represented by sin of omega t minus of pi by 2. Now this can be written as I is equal to V naught divided by L omega, that can be represented by I naught sin of omega t minus of pi by 2. Let us consider this one equation number 1 and this represents equation number 2. If we compare these two expressions, voltage and the current, there is a phase difference value, that is pi by 2. If we observe the graph for an inductor, alternating voltage applied to an inductor, and this represents voltage wave, and here it is a current wave. Right? There is a phase difference, that is pi by 2 between voltage wave and the current wave, and this represents a phase difference between voltage and current. Therefore, we observe the Phasor diagram, that is, and this represents a voltage peak value, and it is omega t at an angle omega t, and here it is the current value at an angle, that is pi by 2. Already we discussed that phasor is nothing but it is a vector rotating in anti-clockwise direction. Here from this phasor diagram we can conclude that current lags behind a voltage by pi by 2. The current lags behind a voltage by pi by 2, or we can represent voltage leads a current by pi by 2, and this is about the alternating voltage applied to pure inductor. The next concept is inductive reactance. That can be represented by chi L. So the inductive reactance is nothing but the effective opposition offered by the inductor to the flow of alternating current, that we can call it as inductive reactance. Here inductive reactance that can be represented by chi L, which is equal to omega into L. So this can be written as 2 pi nu into L. Therefore omega L chi of L, which is equal to, which is directly proportional to that frequency. As the frequency increases, the inductive reactance also increases. If you observe the diagram for that one, chi L frequency, as in frequency increases, the inductive reactance also increases. We are going to observe like this, and this is representation of inductive reactance graph with frequency, and this is about inductive reactance. And even for a DC, for direct current DC, if you observe, so the frequency which is equal to 0, if the frequency which is equal to 0, therefore the inductive reactance also becomes 0 for direct current. So this is about inductive reactance.